All right, do you see my Jupyter Hub? And I'll put up Slack and this channel. So during this channel, it's kind of hard for me to hear what's going on in the room. So if you have questions, maybe post them here instead of shouting them out, because I can't really hear and discern what's going on in the room. Welcome to this session, which is going to be an introduction to machine learning. And this session has two goals. The first is to introduce you to concepts in machine learning broadly. And the second is to introduce you to machine learning in Python specifically, using a fantastic library called scikit-learn, which is, I'd say, the most widely used library for machine learning in Python. All the materials for this are inside of the curriculum folder inside of Rokem-ML. And this, I should say, this session will dovetail very nicely with the session that Elizabeth Dupree will teach on Friday, which will be about libraries in Python that do machine learning with neuroimaging data. So we'll do a little bit of neuroimaging data in this session, but it'll be a very light touch of neuroimaging and a lot more sort of what I'd say is generic machine learning. The notebooks are organized by order. We may or may not get through all of these notebooks in this session, but you can also read them on your own. The preliminaries here is actually not that important for you who are attending a session together with me, but are there more for people who are doing this on their own, who find this this notebook and want to try on their own. It introduces the data set that we will use. So I'll tell you a little bit about the data set that we will use, and then we'll come back to machine learning. So the data set that we will use is the data from the Autism Brain Imaging Data Exchange ABIDE, and this is the second iteration of the ABIDE project. And in this project, about 1,000 scans were collected across multiple different sites, both in individuals with autism and with control subjects as well. And for the purpose of this tutorial, what we're going to use is a processed version of this data. So using the pandas library here, you can read the data. It's in a CSV file. It's in the shared directory. We have a shared directory here that has a data directory in it, and in that there's different data sets, including this ABIDE2 data set, and in there's this tab separated values file, and here I am presenting it to you. It's got 1,004 rows, and so each row represents a single individual. There's the site in which this was collected, the subject ID, their age. The age residuals we'll come back to in a little bit. There's sex and whether or not they had autism. And then there are a bunch of FreeSurfer-derived statistics about their brain. So there are things like the regional area of different regions. Here's left V1 ROI. And then there's cortical thickness, CT, and I believe there is also gray matter volume somewhere in here, and so on. And there's, in fact, 1,446 different columns. This is 1, 2, 3, 4, 5. So these columns that kind of are metadata about the subject are the first 6, and then there are 1,440 different features of the brain for every individual. And this is the data that we will work with in the tutorial, and we'll try to do various things related to machine learning with this data. Okay, what questions do you have so far? I can't see the Rokem now. Okay, if you can't see my folder, that means that maybe what happened was that this was not pulled recently. So in order to make this, pull this, what I'm going to ask you to do is to go to the hub control panel, stop your server. I'll actually do it myself. Stop my server, and then start my server again. And when you launch the server, it should show you these server options. You should use the standard, the default hub user image with the standard, not the GPU machine, but the standard machine. And then when you start that, it should pull the most recent version of the curriculum repository onto your machine. And so this is a bit of a trick where you can kind of reboot things so that you have the materials available, the most recent version of the curriculum. And that should fix that. Let me know if it didn't. Okay. Um, Now let's start talking about machine. So I told you a little bit about data. Let me tell you about machine learning now. Um, Before we start, we need to make sure that we have all these libraries. Indeed, we have them because they're installed um, into the hub. But let's start first with what machine learning is. Machine learning is a field of science and engineering that seeks to build systems capable of learning from experience or learning from data. So the idea here is that we want to build systems that can observe data and then change their behavior based on the observed data. So that's a very broad definition. And in fact, machine learning encompasses a lot of different kinds of engineered systems. It involves many fields of statistics and of computer science and engineering and even experimental design. Some parts of psychology could be thought of as machine learning. And of course, it ranges from relatively straightforward things that we will see today to very, very complicated algorithms, including the algorithms that they're learning about in the other room and even more complicated algorithms. This field has gone from success to success in the last, I don't know, 30 years or so, and has really changed the world in many ways. A lot of technology that we use on a daily basis is based on machine learning. You can think everything from recommender systems in websites where you shop or where you view media. The recommendations that you get are based on machine learning principles. Of course, things like search engines are based on machine learning, but machine learning has also now been incorporated into many, many systems that previously just didn't have those, like things like insurance, risk assessments, you know, pricing of various financial instruments and so on, trading, even in vehicles, you have machine learning systems that are used either, even if the vehicle is not automated, are used in order to sense the environment and use it. They're kind of like learned ideas about the environment to provide information to the driver. So it's really everywhere. There are two common elements to nearly all machine learning applications. The first is on developing algorithms that can learn automatically from the data, so they don't require hand tuning. And that's rather than what previously was what's called sometimes expert systems or these rule-based systems where you explicitly design the rules. You can think of, like, I don't know, a diagnostic system that you build that's automatically diagnosing patients, but it has, for example, you put in, oh, if the temperature of the patient is above a certain number, that means that they're sick, right? And that's a rule that you hard code into the system. Machine learning is supposed to learn these kinds of rules um, automatically and autonomously from the data. The second thing is the algorithm evaluation focuses heavily on the ability to meet objective quantitative targets. And we'll see this throughout the tutorial, what we mean when we say that it's supposed to be quantitative. Okay, and it's different to a large degree from traditional scientific inference, and that's because um, traditional scientific inference has the goal to understand or to explain the data that is observed, and machine learning may or may not include that as an objective, so long as certain quantitative targets are met, and we'll see this in the tutorial as well. Okay, and there's some links here to papers about explanation versus prediction in scientific paradigms, and I invite you to read those, but we're not going to go into this philosophical distinction so much in the tutorial. Instead, let me start carving out the field of machine learning into kind of like sub activities or sub fields for you. The first kind of distinction that we make in machine learning is between supervised and unsupervised learning. And broadly speaking, when we talk about supervised learning, we talk about situations where we have some data about the world, for example, data about our, the data that we have in this notebook. Here from Abide, we have some data, some information about the world. In this case, every row represents a subject, every column represents something about that subject. And in the supervised learning setting, we might have some features of each subject. For example, all the features that are representing different parts of their brain and, kind of features of those physiological quantities of related to those parts of the brain. And then, and we call those features. And then we might have something that we call an outcome or dependent variable, or sometimes the label or the target. For example, we might set as a target the group, whether or not the individual has autism. And by convention, the features are called X, and it's a capital X because this is very often a big matrix. So it has rows, and often it has many, many columns. And the labels are often just one label per person. And so it's designated with a Y, and it's a lowercase y because there's only one of those per person. So this is a big vector. And in our case, for example, the features matrix is a matrix of 1,004 rows by 1,446 columns. Actually, it's only 1,440 because we're only relating to the columns to the right of this column here. So we're only relating to the brain column. So we have a matrix with 1,004 rows and 1,440 columns. And we can say that those are observations on the rows and features on the columns. So every observation has a series of features. And then Y has n observations. It has the same number. There's the same number of values as the rows of the matrix. There's one value in Y for every row of the matrix X. Okay, now in supervised learning, we're trying to use the X in order to learn some rule about how to predict Y, such that if I gave you a new observation, a new row in the matrix, you would be able to accurately predict the outcome Y for that row. So examples of supervised learning include predicting people's chronological age, determining whether or not some incoming mail is spam, predicting a person's rating of a particular movie based on the ratings of other movies, diagnosis of schizophrenia based on genetic markers. So a wide range of things can be thought of as supervised learning. In this case, the supervision here is the fact that the algorithm in question sees a lot of data of this sort, and we tell it, it sees it, and maybe it makes a guess, and we tell it, we kind of supervise it. We say, oh, you got it wrong, or you got it right, or maybe we tell it, you got it wrong by, I don't know, if we're trying to predict chronological age from brain features, we might say, oh, for this person, you got an error of 3 years, and for this person, you got an error of 5 years. And that's the supervision signal. And the algorithms are built to take that supervision signal and use it in order to improve in the next iteration. So it can optimize the solution to this problem. Within supervised learning, there are two, and I'll come back to unsupervised learning in just a bit. Within supervised learning, I'll just tell you there are broadly two classes of, or two kinds of supervised learning. One is called classification, the other is called regression, and that's usually based on the nature of the labels. So in classification, the labels are discrete. They might be, for example, binary, like spam or no spam, or I don't know, diagnosis of schizophrenia or no diagnosis of schizophrenia, or they could be even several different categories, like I don't know, apples, oranges, and watermelons, right? That can be like different classes, and that's a classification problem. In regression, the labels tend to be continuous. For example, the age of the individual could be a continuous variable. So let's look first at regression. It's actually, regression is the easiest of them all to kind of visualize and understand. It's also related to things that many people have seen in the past. So let's start with that. Here's an example of a regression problem. In this case, the label is a continuous variable. It's the y-axis here. In this case, we have an x that's actually has only one feature. So we generated this randomly as a random just random vector of size 30. So there are 30 numbers in here. And those are sort of our independent variables, our inputs, our features. And then we force this to be related to y to be related to x, because we said make it so that y is x times 0.5 plus some noise. So we added some noise, and it's kind of typical. And our regression kind of problem here is to learn a rule that relates y to x, to the input x. We're trying to learn something such that if I see a value of x, I'm able to guess a value of y well. So another way to think about that is we want to generate the best possible prediction for y given knowledge of x. And one way to solve this problem is called ordinary least squares regression, OLS. And here is in Python the solution to that. We start by adding an intercept column. So x is one column here, and then we attach to it another column of ones, and that will represent the intercept. And then we use NumPy. The NumPy library has a linear algebra library in it, and it has a least square solver. This exists in many kind of linear algebra libraries. And so it's going to solve that. It's going to generate a parameter W, or a set of parameters in this case, right? Because x with the intercept is two columns, and that means that we're solving for two weights or two coefficients. One is the intercept and the other is the slope. And here's the best fit line to this data. So we have a line that represents the relationship found through ordinary least squares regression between x and y. The intercept is the value of y when x equals 0. So it's kind of like something like this, negative 0.36. And the second parameter here is, in this case, the slope, how much y changes when x changes by 1 unit, from negative 1 to 1 or from 0 to 1, and that's constant over the entire. So this is linear regression. And it's probably similar to things you've seen before, so this is nothing new. In this case, the equation can be written as y hat equals negative 0.37 plus 0.62x. And this y is got in a hat because that's a prediction. So now if I give you a new x, I don't know, I generate a new x that was not seen before here, you can guess by going to the line what the value of y should be. You might guess incorrectly. I give you a value of x, I don't know, 1, you'll guess that it's a value of, I don't know, something like this, based on this line, based on the prediction. Okay, what questions do you have about linear regression? Let's see. Looks like that problem was solved. Okay, moving right along here. Classification problems are conceptually similar, but in classification, we're trying to make the best prediction with respect to some set of labels. Here's a way we're using in this case scikit-learn to generate synthetic data, blobs in this case. In this case, we have two features, x x1 is the x-axis and x2 is the y-axis in this case. The y is actually the color of these blobs. So half of these blobs are colored in yellow, or they have the label here. I'll put the label up. Half of these have a label 0, and have these are the blue ones, and half have a label 1. Those are the yellow ones. And in the case of classification, we're trying to say based on the values of x1 and x2, just to show you that x indeed is X is a matrix that has two columns, one for every feature, one for every dimension of this space, and has, I don't know how many we made, probably 100 or so here. I'm not sure, maybe we made 100 points or so, some number. So it has some number of rows, same number as X's. So in this case, it's fairly easy to see what you would do. Maybe you would draw a line between these blobs, and you'd say if it's on one side of the line, belongs to one. If it's another side of the line, it's the other. And that's really the classification problem. In the real world, the situation might actually be a little bit more like this, right? Where things are not so neatly separated. And then you need to think a little bit like, what do we optimize? Maybe we try to optimize the classification accuracy. In this case, there might not be any feasible way to really accurately classify. As I mentioned before, you can have a multi-class classification problem like this one, where you have 5 different blobs. So that's also classification. Okay. And those are generally the two kinds of supervised learning that we have. What questions do people have so far? If no questions, moving right along to unsupervised learning. Unsupervised learning is a situation where we don't have labels Y. We only have a set of features X, and we actually don't know how to classify or how to relate this X to some other property of the observations. We really just have a set of features. In unsupervised learning, we might have a goal like clustering, right? So in clustering, for example, here I've created blobs, but I haven't colored them. So maybe you get data that looks like this. It has 2 features, x1 and x2, and you observe that naturally it tends to partition into these different blobs. And maybe in a clustering setting, what you'll do is you'll say like, oh, okay, let's say that let's try to assign labels to these clusters without knowledge of like necessarily the true sort of labels of these things. So as mentioned here, we don't know the true labels, but we can give it cluster assignments nevertheless. It's just kind of a best guess about what's going on. And there are different ways to quantify like how well we're doing this that don't necessarily relate this to labels outside of this. So in this case, we're coloring it based on some guess about the clusters. Unfortunately for us, often what we see, is something like this. Maybe this came from some ground truth, different, truly underlying this. There is some true different groups in the world, but what we'll see is something like this, and that's a lot harder to cluster. In fact, when you look at this, it's not obvious at all how many clusters there should be. Okay, so that's clustering, and we won't do a lot of clustering here. There's a couple of examples here, but I won't go very deeply into clustering. Instead, I will move right along to another form of unsupervised learning called dimensionality reduction. So that's another form of unsupervised learning. In dimensionality reduction, we assume that the data that we're observing, even though we are observing multiple different features, again, in this case, let's say that we're observing x1 and x2, and you can see there's lots of points here. And what we assume, and is often true, is that although the data that we're observing has some dimensionality, in this case, the dimensionality is 2, but in many cases in data that we observe in neuroimaging, the dimensionality is very, very high. We assume that underlying this, there are latent underlying dimensions that are a lot lower. So we assume that there's an underlying process that generated this data that in fact has much lower dimensionality than the dimensionality of the observed data. And dimensionality reduction, as the name suggests, is a set of methods to elicit the true dimensionality of the data based on observations of relationships between different dimensions. Here's an easy example for you. In this case, there's x1 and x2, so there are two dimensions. But in fact, a lot of the variance in this data set can be explained as a function of how far along you are, along the diagonal line here, right? There's not a lot of variance in this other direction. So you could, in fact, squish this and say, let's just look at one dimension. Let's look at the combination of x1 plus x2, right? And call that the single dimension that we're going to look at. So we kind of reduce the dimensionality. We've collapsed from two dimensions to one dimension, right? We're never going to look at x1 and x2 separately. Instead, we're always going to look only at x1 plus x2 as a way to quantify where we are here. So again, nominally this is two dimensions, but how far along this diagonal line we are is much more informative than any other dimension in this space. And we see this all the time in real data, where truly some combination of the features explains a lot of the variance, and we can combine them together and ignore their individual identities, thus reducing the dimensionality of the data. Okay. What questions do you have so far? Let's see. No questions. Okay. Let's go dive into the Abide data set and start doing some scikit-learn then. So I've presented to you kind of a broad sweep of machine learning methods, and now we're going to dive a little bit deeper into technical implementation of some of these machine learning methods using the scikit-learn package. Scikit-learn is a really great package for machine learning in Python. It's very, very widely used. It has the documentation. The documentation is linked from here. Did I just, oh no, here. Documentation is fantastic. It's like really like a textbook in machine learning with examples of all kinds of things like regression, classification, clustering. You can see some kind of familiar names here already. I really recommend going and looking at the documentation. Often if there's a method that you want to use, there would be a good example there for how to get started with that and how to think about the code. In scikit-learn, data is organized exactly the way that I described it before. We have an array of X that we call X often, that is a two-dimensional array of number of samples times number of features. That is, each row is a different observation. Each column contains a single feature. So for example, here, let's take, here we're doing a little trick. We're taking the data that we read. Here we read the Abide data into a data frame called data, and pandas lets us filter that for all the columns that start with fs. So that will select all the columns that have the brain features and sort of extract out, you can see here's the head of that data frame. It's just the brain features. And the head has 5 rows by 440 columns, but we know that there are 1,004 rows in this X all and 1,440 columns with brain features. For unsupervised learning applications, we can use just this X, but for supervised learning, we want some kind of target. In this case, we're going to take as a target the age from the data. So now we have data that's ready for us to use in supervised learning. We have X, which are the brain features from the Abide data set, and we have the ages of every individual. So let's do a classic example in neuroimaging, brain age prediction. In order to do brain age prediction, we need to initialize an object called an estimator. In scikit-learn, all the models are instantiated or implemented in these estimator objects. These estimator objects have fit methods, they have predict methods that then let us present to the model some data in the fitting stage, and then predict some data using the predict method. let's try to do that here. We're going to actually only select 5 features. Let's do this a lot simpler. There are 1,440 features, but we're going to randomly choose some 5 features, and then we had Y. Now we're going to initialize a regression object. So from scikit-learn, from sklearn, this is how in code you write scikit-learn, sklearn. From the linear module, we're importing the linear regression object, and we're initializing this estimator. So, so when we initialize this estimator, you can see we haven't actually given it any data yet. What we're initializing here is an object that knows how to do a linear regression, an ordinary least squares regression, if you give it some data. So in the second, and it has things like, it has attributes that tell it how to do it. For example, in this case, fit intercept is set to true, meaning that it will automatically add an intercept component to the data and will fit not only the coefficients for example, in this case, the 5 different features of this brain data matrix, but also another coefficient for the intercept. It's only when we present it with data doing model.fit xy that anything really happens, any computation really happens. Until now, there was only the notion of how to fit a linear regression. It's only when I call this that parameters are actually set. Okay, these parameters are actually parameters of how to do it. These are the coefficients. So we have an intercept that was estimated to be 53.81. That's the age that we think when all the brain features are at their origin. And then we have some coefficients. You can see that some of these coefficients are very, very small. And that's because we randomly selected 5 different features. It turns out that this feature, whatever it is, and this feature here and this feature here, doesn't really matter for brain age in this case. But instead, there are these 2 features, this one almost -4. So the smaller this value is, the higher the age of the subject. And this one is the same, but almost double or more than double the effect, right? So when this changes by 1 unit, it affects the age twice as much as when this changes by 1. So that's the interpretation of this. Here's written out in math. And so now we fit this model and we have some parameters associated with brain features. The next thing that we want to do is then generate predictions. How do we generate predictions? We give the model, or rather the model predict method, we give it an X. In this case, we're going to give it the same X that we used for fitting the model. And that then predicts the age of the subjects. So it gives us back a predicted Y. This is like the Y hat that we saw here. Right? So this is Y hat. And we can visualize the predicted scores against the true scores. This one will draw that for us. So here we have, this uses a library called Seaborn, which is a high-level plotting library. We did some data munging in here to get that in the right place. But once we do that, we have on the x-axis the predicted age, and then on the y-axis the true age. And we can look at that and see, okay, well, it's not actually that bad. There's, it's not great, but there are some cases where it hits. The age range is a lot smaller in the prediction than in the true. You can see that the true ages range from about, I don't know, 5 maybe to 65 maybe. And the prediction is a lot more conservative. It says, well, it says that some of these haven't been born yet. That's a problem. But then it never predicts, it almost never predicts above age 27 or so, and only in one case above age 30. So it compressed it. But, there's if we computed a linear regression, if we computed a correlation coefficient between true and predicted age, it wouldn't be too bad. So this is just kind of to show you how powerful scikit-learn is. This is everything we did, right? We initialized the model, we fit it, and then we generated predictions, 3 lines of code. Now you might look at this and say, well, how do we know if this coefficient is statistically significant? And that's not what machine learning does. You could do that. There's another library called stats models that will do something like that for you. It will, generate things like the coefficient. Here's the same coefficient, right? Because it also does linear regression. And then it will give you a t-value, some, confidence intervals and so on. But that's standard statistics. That is not what machine learning does. So we're not going to pause on that too much. Instead, in machine learning, we quantify the performance by looking at the predictive quality or the predictive goodness of fit. One way to look at that is using something called the R2 score or R squared or the coefficient of determination. Out of curiosity, I'm going to do a little activity here with you. Let me go into Slack and type, and then you will do a thumbs up. Who has heard of the coefficient? Give me a thumbs up if you've heard of a coefficient of determination, and give me a thumbs down if you've never heard of this thing before. Okay. Y'all have heard of this, or everybody's thumbs up. Okay, so this is the coefficient of determination. And we can do that. In fact, there are scikit-learn implements. There are R2 score function that when we call it, I'm up here, sorry, it calculates the coefficient of determination. And this is the coefficient of determination that's associated with this prediction here. So, 0.2, 20% variance explained, that's, I don't know, depends how you think about it. But it is a quantitative value, so we can use that quantitative value in order to assess the goodness of fit. So that's kind of like what we're going to go towards here. In fact, scikit-learn objects have so these estimators. If I initialize an estimator called linear regression, I can immediately fit it and then score it. And the linear regression, every estimator has a different score that's associated with it, and the linear regression estimator has the coefficient of determination associated with it. So if I call score with X and Y, I get immediately a number there. Okay, let me pause here and see what questions do people have so far about the mechanics of using scikit-learn or quantifying goodness of fit or other things. Okay, I am going to skip over this classification example. There's an example of classification here. You can do classification with scikit-learn as well and evaluate classification performance, but I'm not going to do this here because for the sake of time, just so we get through everything. Okay, so now we've done this with 5 features. The question is, can we do better than we did, right? We got 20% variance explained. Can we get more variance explained, for example, by adding more features? We have a lot of data, right? Our data is very, very high dimensional. In fact, part of the goal of these tutorials is to show you that machine learning is a set of principled methods to deal with very high dimensional data. So what if we, looped over these features and selected randomly 5, then 10, then 20, then 50, then 100, and so on. And each time we ran linear regression 10 times, and we averaged the performance. So we fit it, and then we score it, and we put that in the results. And once it's done, we kind of average for every number of features. So now it's going through, and it's fitting 10 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 9 linear regression models, these brain age models, and it's scoring each one. It's going to give us the results in a big matrix here. And in the end, we're going to average and just kind of look with one standard error bars, like how well did this model perform with different numbers of features, like can we do better than the 20%? Okay, it's chugging through. So this is a good time if you have any questions about anything I said so far.
I do have a question. So
Yes.
how do you determine if an R2 score is good enough or not?
How do I determine that the R2 score is word that I didn't hear or not?
Good enough or not?
Like if the value is like line between less than 0.5, probably is near to one.
Oh, how do I determine that like 0.2 is good?
Yeah,
Oh, that's a little bit hard to say, right? Like, depends a little bit on what you're trying to do with this. If I was trying to, like, I don't know, do a census using brain age and I had a variance of 20, or I don't know, like quantify like, use this in order, why did that happen? Use that in order to determine whether a person is eligible to drive, for example, this would be terrible, right? Because it's really not a very accurate way to predict age. But if I was using the brain age to do something else, like for example, people will use brain age to, for example, assess whether a person is older than their brain is older than their chronological age, and maybe there's something that's very sensitive to that. Maybe 0.2 is enough to do that. So really it depends on the problem. And there's no like, oh, this is good enough. There's only this is better than that in some sense, right? So it's more comparative kind of thing. Is it done? It's not done yet. Okay, let me see. Let's try a little guessing game here. What do you think we'll see when this is done? What will the curve look like that relates model goodness of fit as quantified with goodness with coefficient of determination as a function of the number of features? Is it going to be who thinks performance will increase with the number of features? Who thinks it will decrease with the number of features? Who thinks it will stay the same? Okay, it's done. So now we can see. Okay, performance does increase. In fact, it increases so much, right? We started out with 5 features and about 20% explained. By the time we're up at like, I don't know, 400 features, we're close to 80% variance explained. And by the time we've gotten to all of the features, we have 100% variance explained. So on the one hand, this looks great. On the other hand, there's got to be something wrong here because it predicts age perfectly. And even if you just think about this data set, surely some of the ages are recorded incorrectly, right? There's clerical errors or whatnot. So there's something here that doesn't make sense. And that is the next thing that we will talk about here. Okay, the thing that we will talk about is called overfitting. And this here was an example of overfitting. But let me explain to you overfitting a little bit more slowly by looking at some examples. So we're going to use scikit-learn's linear regression again. Now we're going to make some synthetic data. This data is a little weird. We're going to make some data. X is going to be some random numbers, and then Y is going to be, and this is going to be just one feature in this case for X. Y is going to be a quadratic, have a quadratic relationship, right? This is a quadratic relationship with X. So now if we generate some data using this make XY function here, it looks like this because it has a kind of the quadratic makes it have this kind of U shape. Now, suppose that we try to fit this data with a linear regression, right? We don't know what generated. There's a process here that we can see here, but suppose that we don't know. Suppose that we got this data and we don't know what process generated this. And we naively did what we did before, which is to fit linear regression to it. Well, it would fit a straight line. So here we have linear regression for scikit-learn, and it's fitting X. In this case, we need to do this in order to make this into a column vector. And we look over a range between the minimal and maximal x, and we predict within this range to create this regression line. And you can see that it does not so great, and that's because it's not doing the thing that it's trying to fit a model that's incorrect to this data, because the data was generated using a quadratic, and this we call underfitting. This is underfitting the data. The model that we are using is less complicated than the model that generated the data. Now, we can also go and we can fit a much more complicated model. Let's fit a model called a polynomial regression model. In a polynomial regression model, we generate regressors that are x squared, x to the third, x to the fourth, and so on. So we generate a set of regressors for the data that are a set of polynomials. This is done here using some code. I won't go into the details of the code except to tell you that scikit-learn, because polynomial regression is a common thing to do, the preprocessing module has this thing called polynomial features, and also we can generate what's called a scikit-learn pipeline. Here we're generating a pipeline where the first part is to generate polynomial features from the x that is provided as input. And then the second step is to do linear regression on the polynomial features. So this pipeline together is a polynomial regression pipeline. And that's what's returned when you make a pipeline. When you use this function, make pipeline, you give it a degree, the degree that you want to use. In this case, the default is 1, but you can set it to other degrees as well. If you give it degree 10, it will generate x squared, x third, x to the third, x to the fourth, x to the fifth, and so on. In this case, we're going to do, and you can play with this on your own. Let's make a pipeline with degree 10 and fit it. Oops, sorry, I need to do this first, and then that. All right. In this case, it fits the data really, really well. And that's because we had a quadratic that generated this, and we gave it degree 10 polynomial. And if you give it the up to degree 10 polynomial, it can kind of hug every single point in the data, or very closely hug every single point in the data. In fact, it's so flexible that it can go down in order to go up and hit this point up here precisely. Now, surely this is a little bit contrived. On paper, this model fits the data a lot better than our linear regression, but it you can understand intuitively that bending this thing out of shape just to fit this one point is wrong. And we can demonstrate that by making another data set using the same process. So here we're going to use the makeXY function and generate another data set. And so now the points are a new data set generated using the same mechanism, the same underlying process. makeXY generated 30 new points. And the line is the model trying to predict the first set of points. Now there is no point up here to fit. So this deviation of the model all the way up here to values above 20, that becomes a huge error in predicting, the actual data. The important part here is that we fit the model to one set of data, then we generated another set of data from the same process. And really, when we generate predictive models, what we want is something that will do well in this setting. It will fit well to a first set of data, and then it will predict well for subsequent data, right? If we're generating a machine learning system that should predict the age of a person who shows up at the clinic and gets a scan, we want to be able to predict well for that person, not for all the people that the machine learning models saw before. And machine learning models, including these linear regression, polynomial regression models, are very, very powerful. And so that means that they can fit data very, very well. That is, they can, if you give them enough flexibility, they can fit very complicated, even very high dimensional data really, really accurately. Was there a question? No. In fact, that's what's happened. That's exactly what happened here. We had data set, I'll remind you, with 1,004 subjects and 1,440 features. And by the time we had more than 1,000 features available to us, what the model did and this is linear regression, was fit a hyper surface in more than 1,000 dimensions that passes exactly through every single point in the data set. So because you have so many dimensions, you can find a hypersurface, even if it's a linear hypersurface, that passes precisely through every point in this data. And that's because you have more features than observations in this data. And in this case, it overfit perfectly. Okay. Here's an example. So now we're fitting, using, in this case, polynomials up to degree 2, and you can see that works well, both in the, that works well even when we look at held out data. In fact, you can create a little interactive widget here. We've created an interactive widget where we fit some model to the training sample, and then we try on a test sample, and you can try what happens if you go to degree 4 of MSc. Degree 3 is not bad. Oh yeah, it doesn't actually matter that much. Right. So you can try playing with this. Whoops. If you have like degree 10, and you can look at the mean squared error. MSE here stands for mean squared error on the training sample, on the test sample, and sort of ask yourself what should be the relationship between those. So that's the concept of overfitting. The question is, well, how do we overcome this kind of problem in a systematic way? Before I go on to that, what questions do people have? Okay. How did we determine how many times? Okay. This is a question about this experiment where I ran. It wasn't like very deeply thought through. In fact, it was just so that things would stabilize. So if you get some weird selection of features on one iteration, it wouldn't affect the overall effect that we see here, that if you randomly select more and more features, you get better and better performance because of this overfitting effect. Okay. Then there's somebody here who's curious about unsupervised clustering. Do you mind if I punt this to later? Because I have a kind of like agenda here of getting through some things, but let's talk about unsupervised clustering later on. Okay. There are a lot of things that are going to be in common between unsupervised learning and supervised learning, and the focus here is to give you a sense of how machine learning methods deal with these problems with very high dimensionality in a systematic way. And so the focus really here is on this supervised learning, and specifically on regression problems. I'm going to mostly show you those, and then we can talk about other kinds of problems later on. Okay, so how do we deal with overfitting? Actually, let me see. Any more questions? Okay, so how do we deal in a systematic way with overfitting is the topic of the next notebook, and the answer is using validation, in particular using a procedure called cross-validation. So we'll start by importing some things and reading the data. Again, we'll have X all be all the features from the free surfer and Y be the age. Scikit-learn gives us what we saw in our previous notebook is that it's often good to look at a separate held out data set that we call sometimes a test data set when we fit a model and we're worried about overfitting. So we have a training sample, that's the sample on which we're fitting the data or fitting the model. And then we have another sample for evaluating that. And that's really what we're going to do in cross-validation. That what I just described is cross-validation. You train on one set and you test on another set of data. And scikit-learn, because it's such a useful procedure, scikit-learn has a utility called train test split. It will take data like X all and Y. It'll take some value of the training size that you want to do, and it will split it up into X train and X test, Y train and Y test. So here, let's run that. What you see is that the X train is, so what it does is it splits the matrix up by rows, and it doesn't split it to top half and bottom half. Instead, it randomly selects, in this case, 50% of the rows, 502 rows, and it selects from Y the corresponding entries. So the nice thing about this, this utility is that you give it both your X and your Y, And what you get in X train is a set of training samples that are matched to the Y train. And in X test, you get a set of observations that are, or a set of features that is matched to these labels or variables in Y test. So now you can fit your estimator using the training data and evaluate its performance using both the training and the test data. And that's what's happening in this. So here what we're doing is we're starting a linear regression, we're fitting it with X train and Y train, and then we're scoring it both with X train and Y train, the data that we used for training, and also with the held out test set. And what you can see here is that it fits perfectly in the training sample. That's really what we saw here, because we're giving it all of the features, but it's failing miserably in the test data. And that's because it overfit exactly to the training data. And when we presented it the test data to score, it couldn't do anything with that because it really just failed miserably there. Out of curiosity, give me a thumbs up if you're surprised that R squared is negative here. If you're surprised, just give me a thumbs up. If you're not surprised, you can give me a thumbs down. Someone is surprised. Okay. Okay, a lot of people are surprised that it's R squared is negative, and it is sometimes surprising, and that has to do with the definition of the coefficient of determination. The coefficient of determination can in fact go negative, and that's because the coefficient of determination, in contrast to say the Pearson correlation, the way that it's calculated, it allows for negative values, and that's because it's comparing the variance that is explained in the variance of the errors in the prediction to the variance of the data. And the variance of the error of the predictions, the sum of the squared errors, that can be arbitrarily large. And so when the sum of squared errors is larger than the variance of the sample, the coefficient of determination goes down. Let's look at the standard definition of R squared just to clarify that. Yes, the R squared, the coefficient of determination is 1 minus sum of squared residuals, that's the sum of the squared of the errors, over sum of squared totals. That's sum of squared totals is like the variance of the sample. So if you have a sample where the variance is not very large, but your model is so bad that the errors are really, really large, then you'll get a value that is larger than 1 here, and 1 minus this value will go negative. So that's the reason that the coefficient of determination can go negative, and here it's explained here as well. So in this case, it overfits so badly that coefficient of determination is negative. Let's see, a little guess. When R squared be equal to 0? And I told you that it can be negative, and certainly it can be any number between 0 and 1. When will it be equal to 0? Does anyone have a guess? You can type it in there. Just based on the definition that I showed you of the R squared. This definition of R squared. Anyone have a guess? Or maybe you know the answer to this? Okay, I see people are typing. I'm waiting with bated breath to see you come up with them. Okay, R squared, I'll give you the answer. The R squared will be equal to 0 exactly when, for example, the model predicts the mean. And that's because if you look at this definition, the sum of the squared of the errors will be exactly equal to the sum of the squared total when you guess the mean every time, because the sum squared of residuals relative to the mean value is the variance. That's the definition of the variance. So in that case, R squared. Back to this. Okay, well, in this case, we took all of the data. What happens if we take less of the data? Let's take, I don't know, let's sample 200 features and repeat this procedure. Well, now the R squared in the training sample is not as good. It's not 1 anymore, it's 0.8. In the test sample, however, it's 0.46. So that's much, much better. There's still some gap. It's kind of overfitting here, but not as terribly. And certainly it's not erring as much. So if we take a much smaller number of features, then we can do a lot better in the test sample. And this is cross-validated, fully cross-validated. So what we've learned now is that the model is capable of predicting age reasonably well in subjects that it hasn't seen before at all. So that's kind of encouraging. Now, when we split the data into training and test set, that lets us evaluate the model like we did here on separate data, but it also increases our propensity to overfit to the training data because we've carved out the data into like just half of the data. So we have a lot less data to work with. And to solve that problem, people have come up with this procedure called k-fold cross-validation. In k-fold cross-validation, we do the following procedure. We repeat this train test split k times. For example, if k is 10, we repeat it 10 times. And in the first time, so we use most of the data, 90% of the data in this case is used as training data. So instead of splitting the data into half and half, we split it 90-10, and we train the model on the 90% that set as training data, and we evaluate it on the remaining 10. And we repeat this procedure 10 times, leaving out a different 10% of the data to be test data every time. By the time we're done with this, every single observation in the data set has been in the test fold, in the test set once. So we can actually evaluate the error on the full data set as well. And that's called k-fold cross-validation. And I won't show you we coded up this here very explicitly so you can see it, but I'm going to go to k-fold the easy way. And that's using a little utility called cross-val score. What cross-val score does is it takes an estimator, a scikit-learn estimator. It takes some x small in this case is only 200 features. It takes some y, and it takes a number of a k, the number of cross-validation or folds that you want to use. And then it calculates an R squared for every held out fold in this case. And you can then, you can average these in order to get an average. So you kind of get like an average across, in this case, 5 different samples, or 10, and get an average across 10 different samples. So this does cross-validation. This cross-val score it splits the data into train test, k times. Each time it fits the model, and then it scores the held out test set. And then it gives you a cross-validated R squared here. And this cross-validated, I should say, this cross-validated R squared is a true R squared. It's not overfit to the data because it's done by observing test data that wasn't observed when the model was first fit. So that's it. This is kind of like a very, very fast way of doing full cross-validation on an estimator. And one of the nice things about scikit-learn is that it has many different estimators, as we'll see in the next notebook here. And you can plug in many estimators here to see, okay, let's see if this estimator or that estimator works better. Okay. Let's see. Okay. I'm going to skip over this cross-validation isn't a panacea for the sake of time, because we only have 25 minutes left, and there's one more big chunk here that I want to make sure that we get to. But I do recommend going and looking at that. It shows you something that is important to think about. Instead, I'm going to skip forward here to what's called the learning curve. Scikit-learn has these utilities called learning curve and validation curve that allow us to wrap up the cross-validation functionality and try out different kinds of settings. For example, here we can plot a learning curve with different training sizes. So here we're using different training set sizes as a way to as a way to look at the impact of the number of observations on cross-validated R squared. We're doing this with linear regression, still with this kind of brain age prediction. This learning curve, what it does, it takes an estimator, it takes X and Y, and then it takes some kind of thing that you'd like to iterate over, in this case, the size of the sample. And then it'll plot that for us. And what we can see here is that as the sample size goes up, so if we start with a very small sample, we get very, very highly overfit, a highly overfit situation. The training set is overfit. In this case, we have 200 brain features. So it's not surprising that it overfits with only 100 samples, right? This is the same situation that we had up here. Many more features than we have observations. And then it goes to 200, 400, and 800. So we get very overfit, right? It's perfectly fit to the training and disastrously fit to the test in 100 samples. Then at 200, they get closer. And as we increase the sample size, the training and the test get closer and closer. So what we see here is a way to quantify how training and test converge as the sample size increases. So our models become more and more accurate as the sample size increases, and that's not too surprising. Okay. We're going to do this now with different sets of features, right? So I'm repeating this same kind of experiment here. Here I showed you that as the sample size for 200 features, as the sample size increases, the model prediction, the model becomes better and better in the sense that the test R squared becomes larger, the training and test become closer, so it's less and less overfit. In fact, the model is better, the R squared is in the test is higher, and that's our goal, is to get high test R squared. Here, what I'm showing you is that when I repeat that experiment with different numbers of features, I get different kinds of characteristics. If I use 5 random features, both the train and the test R squared are just not that great. They're between, 0.2 and maybe 0.3. If I select 30 random features, on the other hand, it becomes a lot better, especially when we have larger numbers of observations. And then if we use 100 random features, then it's catastrophically bad for small samples, but maybe it's even better, but with very large error, for the very large samples. So we have this kind of interesting interplay between the number of sample and the number of features that we used. And we'd like to be a lot more systematic. So what this shows is you can start doing experiments where you vary which features you use and how many features you use. And that's really the goal of machine learning, or one of the goals of machine learning, is to let you do systematic experiments with your data. Let's say in this case with this high dimensional brain data, such that you're able to do experiments and figure out exactly what setting you should use for the model so that you're not overfitting and so that the model predicts as well as possible. Now we can go and become even more systematic about this, which is what we'll do in the next notebook. But before I go to that, let's see what questions we have at this stage. Are same splits and cross-validation always required to be able to do ML? I assume that you would need a relatively large sample. Yes, so one of the things that is typical for machine learning is that you do usually need large samples, if only for the reason that you're going to start splitting your data across train and test splits, and once your sample is small, you're going to be in a tough spot, and you're going to be starting to really be shaving your data too thin to be able to fit models. So you do need lots of data. Machine learning methods are notoriously data hungry. In fact, one of the lessons kind of learned from machine learning over time is that sometimes if you have a model and you're trying to go more and more and more sophisticated, you can't do better than you would do with a simple model. I can share some recent papers that demonstrate this. It's very, very hard to get much better with a very sophisticated model if your data is limited. In fact, for better performance, it's often better to go and get more data than to get a very sophisticated model. So it goes. Just wondering, will there be bias in such a situation when you're doing cross-validation, I think? Not always, usually required if it goes tests. No. So I think the question is whether this kind of evaluation is biased, and the answer is no. If you're using a true held out test set, then this R squared is a good guess of the R squared that you would get on some new data. It's not biased in that sense, at least. In fact, it's a good guess if you do this many, many times. It's a good guess for the R squared that you would get if your sample once the sample size is large enough, I should say. This is a good guess of where the R squared will eventually converge, right? An unbiased estimator is an estimator that comes closer and closer to its population value as the sample increases. So here we're increasing the sample and R squared goes up, and that indicates to us that this relationship, because R squared is unbiased, it indicates to us that if the sample went really, really, really large, we would eventually converge on kind of like the true population value of the relationship between brain data and in this under this linear model and age. Okay, what other questions do people have? Okay, let me then go into the last notebook here. There's one more I don't think we'll get to dimensional reduction. Well, let's see how we get on here, but this one is the most important one. The idea is that we want to be systematic. So we've come up with a way to do systematic experiments here where we can evaluate R squared of a model by holding out some test data and training on some trained data and then checking. That's called cross-validation. This lets us do a set of systematic experiments. What we're going to show next is that you can, in fact, use principled methods in order to select the model that you will use. And I'll show you an example of that. But there are many ways in which this happens in machine learning. This is going to be an example that will also demonstrate some important kind of principles that are important to take into account. And the first kind of principles that we're going to introduce here are bias and variance. So imagine that you have some model, and here are observations, or rather, these are predictions. Let's imagine that our predictions are sort of like we're throwing darts at a dartboard. And if our predictions are correct, we hit the dartboard right in the middle. There are two ways that our predictions could be wrong. One way that we could be wrong is if our model always hits the dartboard far away from the center. And that's called bias. If our model is biased, it's firing away at the wrong, kind of like it's biased relative to the true value. Maybe this is a brain age model that always underestimates the age of the subjects, or always predicts that the age of the subjects is closer to the mean than it actually is. It tends to go towards the mean. The other way that the model could be wrong is by introducing a lot of variance. Variance would mean in this case that for different individuals, our errors are different, but overall our errors are large. Right? This model is not biased. On average, it's predicting the right age. Right? The errors are on average kind of like distributed in all directions, but the variance is high. So for every individual, we get a large error. And then of course there are models that have high error, high variance and high bias, and those are even worse. This is going to have an even worse error than, you can see that it has a worse error than this one, even for similar amounts of bias, because you get error both from bias and from variance. Now, it is the case that there is a trade-off between bias and variance, and I'll show that to you here in a little bit. And that's something that we can exploit. In fact, we can come up with some model where we introduce some bias so that we can reduce the variance. And there's a set of methods that do that. I'll show you, instead of going through this car example, I'll show you how this works in practice in what we call penalized regression or regularized regression. The idea behind regularized regression is that we will introduce some bias into the estimates of the model, and by that we will reduce the variance. And if we're lucky, then we will find the right amount of bias to introduce that will reduce the variance just so that the errors will become smaller and we'll get a better model that way. How do we do that? So here is the cost function for ordinary least squares regression. The cost function is our true y. For every subject, we have a true y, the age of that person, for example. And this here, the sum of beta j xij, where xij are the individual brain measurements for that subject. This is sort of like the linear sum of their brain features summed by the coefficients that the model found. So these are the model parameters. You might remember from one of the first notebooks, we had this kind of equation. I'll show it again because it's kind of important. See if I can find it quickly. Yeah, this one, right? So we had x1, we had some number x1 plus some number x2 plus some number x3 plus some number x5. These numbers are these coefficients, are these beta coefficients. So this is our guess based on the model of the age of subject I, and we subtract those from each other and we square it. So that's why it's a residual sum of squares, and we sum it over all the subjects. So we get the cost function for ordinary least squares is the residual sum of squares. When we fit ordinary least squares, what it tries to do is to reduce this number as small as possible. Now consider a slight variation. We take the residual sum of squares and we define a new cost function, which is the residual sum of squares here on the left. This here on the left is the residual sum of squares, plus another cost function. It's got a little parameter lambda attached to it, and then it's the sum of the absolute values of the beta coefficients. So in this case, in addition to the residual sum of squares, we're also penalizing on the absolute value of the beta coefficients. We want the beta coefficients to all be as small as possible. So we're introducing some kind of bias where we're kind of pushing down all the beta coefficients. That's a form of bias in order to kind of maybe reduce the variance. Here's another one. It's very similar to that one, but in this case, instead of penalizing on the sum of the absolute values of the betas, we're penalizing on the absolute value of the squares of the beta coefficients. So these are closely related, but they're not identical. And these entail different kinds of bias. The first kind of bias here is called lasso regression. If we implement this bias and we implement this cost function, we get an algorithm called lasso regression. If we implement this second kind of cost function, we implement something called ridge regression. And both of these are forms of regression that penalize, in addition to residual sum of squares, by something that depends on the coefficients. So let's take lasso regression. This lambda, because lambda is a keyword in Python, instead of lambda, this is the way we write this in math. In code, we will write it as alpha. So in this case, we're implementing here a function called plot coefficient path, which takes an estimator, it fits that estimator to some data, and then it takes the coefficients and it plots them. So let's apply that to the data. We're going to do that with 200 features, and we're going to do the brain age prediction, and we're doing this with lasso. And so here what we have is each line here represents a coefficient for one of the 200 brain features. The x-axis represents the penalty, right? It represents the lambda, how much we're weighting this sum of the absolute value of the coefficients relative to the residual sum of squares. Now you can see what happens is that if alpha is very, very small, we get coefficients that have some values. But as alpha grows larger and larger, what lasso will tend to do is to shrink the coefficients towards zero, such that by the time that alpha is very, very high, all the coefficients are zero. Okay? Ridge regression does something similar. Oh, here's ridge regression. But it just looks a little bit different. It does it in a different way. And that's because it uses this this penalty on the sum of the squared coefficients. So it has a slightly different, but the same principle applies. If the alpha penalty is very small, the coefficients could be large. And if the penalty is very large, the coefficients grow smaller and smaller. Okay, why is this important in the context of predictive performance? The reason this is important is that twiddling this knob of the alpha lets us select different kinds of models. The effective number of parameters is smaller and smaller the further to the right you go. In fact, you can see that what happens here is that as you go from left to right, lasso essentially shrinks to zero, lots of coefficients, and leaves only some. So if you start out here, you have lots of coefficients that are activated, but by the time you're up here, only very few of the coefficients are activated, and most of them have already shrunk to zero. So that's a form of model selection because it says choose these coefficients and not those coefficients. And the same happens with ridge regression. The model that we have here is very different from the model we have here. So what we have here are kind of like knobs that we can twiddle to select different kinds of models. Let's see how that plays out in the setting of generating these kind of learning curves that you saw before, or validation curves. Okay, here what we did is we fit different models, and now what we're doing is cross-validating each model. We're going to go, we're doing 5-fold cross-validation each time, and we are testing different values of alpha. So on the x-axis here, we have the penalty alpha. For comparison, we have the ordinary least squares on the test set. This is kind of our baseline performance here. Ordinary least squares has no addition of this penalty. What you can see is that, and lasso has, right, it has a penalty. It starts with a very low penalty, and then the penalty increases. What you can see is that by the time the penalty is very, very high, performance of lasso is very, very bad. In fact, it's got 0 R squared in both in train and in test. And that's because by the time you've gotten to very high values of alpha, lasso completely ignores the data, right? Because we told it penalize on any value of the coefficient growing, it's just going to set all the coefficients to 0 just so it doesn't have to pay this additional penalty. And in fact, it's just going to ignore the data. Because we have an additional intercept term here, what it's going to do down here is it's going to predict the mean age for everyone. And as I told you before, when you predict the mean age for everyone, you get a coefficient of determination of 0. And that's because the mean prediction, the errors on the mean prediction are equivalent to the variance. And because of that formula of the coefficient of determination, when you get the residual sum of squares equal to the variance, you get an R squared of 0. So that's up here. But in between, there are actually situations where lasso does better than ordinary least squares, right? Up here, in intermediate values of alpha, in fact, there's an optimum to this curve. There's a particular value of alpha that gives you the best value of R squared, test R squared. This is where the model performs the best. So there is, in fact, an amount of bias that we can add that removes enough variance to trade off those things just optimally so that we get a model that is more accurate than we would get in the naive case where we used ordinary least squares. And because we're using cross-validation, because we're doing these systematic experiments, we can discover that setting. The way we think about this is that in this case, alpha is a hyperparameter. The parameters are the model are these betas are these coefficients. And then there's a hyperparameter that determines how the model is fit internally. And what we're doing here is an experiment in order to determine the value of the hyperparameter. Now, you can have models that are a lot more complicated and have a lot more hyperparameters. And then you'll need to do experiments that are a lot more complicated than the experiment that I showed you here. But the same principles apply. You'll always want to do cross-validation and meticulously do that in order to make sure that you don't get leakage of information from the training data to the test, sorry, from the test data, leakage of information into the train data. So you want to split your data as early as possible in the training procedure so that you're really holding out the test data and not leaking information back. Remember that Russ mentioned in his talk this one example where people had leaked information back in this case of, I think, suicidality prediction. You want to try to avoid that as much as possible by splitting your data as early as possible in the training. In fact, in some cases, we'll set aside a test set before we even start doing anything. We'll set aside a test set that will be our sort of last evaluation test set. And that's because you can do a lot of these experiments and you can kind of play a lot with the data until you find the right setting and hyperparameters. But if you're doing this, you can, if you separate your test and the train data, you can do lots of cross-validated experiments to find the right setting of your hyperparameters that gives you a model that gives you good prediction on a held out test set. And that gives you a way to kind of like an experimental method to figure out how to fit these models in the real world. And like I said, scikit-learn has a lot of different models. I showed you here models that are relatively simple because they're linear regression models, but they're also nonlinear models. And there's a few of those in this, actually in this very notebook, there's some kind of random forest models, more complicated ones. I'll just show you, this is what the validation curve looks like for ridge regression. Same principle applies. If the alpha is very, very high, you get 0 coefficient of determination, but there is an intermediate set of values. And now you can also ask, is this intermediate value of R squared, is it better than lasso? You can kind of compare lasso and ridge to each other. It looks like maybe ridge is better, but I'm not 100% sure. So anyway, you can start comparing different models to each other and then do, I don't know, nonlinear models like these random forest models and other complicated things. You can combine, in fact, and if you want to take a look on your own, since I won't have time, I think we're finishing in 2 minutes. Is that right? So I won't have time to show you. You can combine unsupervised learning with supervised learning by starting by taking your data, doing dimensionality reduction first, and then applying a linear regression to the dimensionality reduced data. Again, you'll want to be really meticulous to split your test and your trained data before you do your dimensionality reduction so you don't get leakage. That's one of the ways that leakage happens, is that people use dimensionality reduction methods first, and then they use it on all the set, and then they split their data. And that will be a grave mistake to make. But you can look at that. So you could build much more complicated kinds of ideas, but it all comes down to really doing experiments like this experiment where you rule the things and see which model can be more accurate in the cross-validation setting. Okay, I'll stop here and open this up for questions. Do we pre-process training and test together, or do we split even before that? That's, yeah. You don't want to pre-process together. You don't want if the pre-processing involves something like determining the correlation between features, right? One way to do dimensionality reduction is to look at the correlation between the different features. If you're doing something like that, what you're going to do is correlate using both the train and the test set. And that's a form of leakage from the test set. How do you determine which is better, lasso or ridge? You compare those, on the R squared. I didn't plot them together, but I think this is maybe, I don't know. I don't know if this value, I don't know exactly what this value is, but I think maybe this one went a little higher here. I'm not sure. You might also have other kinds of considerations to choose lasso or ridge. Lasso does very nice feature selection. I mentioned this, that by the time your alpha is pretty high, it's killed a lot of the features. It's set to 0, a lot of the features. Ridge doesn't tend to do that. They all kind of go to 0 together. So if you want to do something like feature selection, like determine which of the brain features are the most important for brain age prediction, then lasso is nice in the sense that it will give you a sparser solution. Okay, what other questions do people have? Feel free to post more things here in Slack. I think we'll go do a little coffee break here and come back in half an hour for the next lecture. I'll come back here. I'll do my own coffee break here. I'll come back. If you have more questions, just post them here and I'll reply on Slack.